Hi, everyone. It's a pleasure to introduce today the second water webinar focusing on technology. And so last session, we have been focusing on aspects of decentralized treatment and extreme decentralization to host level and how that will drive innovation. And we've also been looking into how the new smaller distributed systems that are coming up in the water sector are going to cause also, at least for water, what would be perceived as a revolution in data management and the tools that we need around this. So the webinar of today complements this technology vision with two very different talks that I'm delighted to announce. So the first presentation will be by Dr. Peter Fiske from Lawrence Berkeley National Laboratory in Berkeley. And so Peter Fiske is the director of the National Alliance for Water Innovation, as well as the Water Energy Resilience Research Institute. And in this capacity, he is a very well-known speaker, keynote speaker. He's also an author. But in this capacity, he's thinking very much about at which scale do we need to deploy technology? And what is this interrelation, this nexus that is, we, for example, call the water energy nexus. And I've taken one of his slides as the background now. So Dr. Fiske will also look at the US level, in part at how large technology, smaller technology will intertwine to meet the goals we set forward for the water sector. In the second presentation, this webinar, we're going to make a bit of a quantum leap. And the talk of Dr. Simon Albert reminds me a bit of a trip I took a long time ago to Borneo in the framework of a water project. And we visited islands where the drinking water supply to the town looked something like this. From the hill, cut pipes of bamboo were bringing the water down to the village, and that was the water supply. And so this is linking with Dr. Albert's talk in a way that he'll be talking about the challenges of water management, of water supply and impacts in areas like the Pacific. So it's really bringing these societal aspects together from a different viewpoints, also for different areas than we typically think. And so with that, we've seen, I think in the past webinar and this one, we've seen and will see very different viewpoints on what is needed to bring a sustainable water supply for all. I hope you enjoy the presentation.
Hello, everybody. This is Peter Fiske. I'm the Executive Director of NAWI, the National Alliance for Water Innovation. And I wanted to give you all this introductory description about the program and tell you how you can get involved. First of all, I am here in California, in the Oakland Hills, and in fact, I'm at Lawrence Berkeley National Laboratory. Lawrence Berkeley is in the San Francisco Bay Area, in the eastern part of the Bay Area, right behind and up the hill from the University of California at Berkeley. My colleague David Sedlak is down on campus, and I and the rest of the NAWI team are up here on the hill. Now, for those of you maybe not familiar with the national labs, you might be curious about what are these national labs, especially relative to industry and relative to academia, and why are they suddenly getting so interested in water? Well, national labs in the United States fit in a very interesting middle ground between universities and industry. On the left, universities, by their nature, are focused on education and early stage discovery, basic science, and relatively early stage applied research. Industry, on the right-hand side, of course, takes market-ready technologies and develops them into businesses with repeatable and scalable value propositions. But between the community of innovators at universities and the community of business people in industry, we have what is known as the Valley of Death, this middle zone where you have technologies that are proven to work at the bench scale, but they don't have enough validity to suddenly be taken on by industry. And it's in this valley that the national labs sit. The national labs specialize in taking high-risk, early-stage technologies, and especially technologies that need to be demonstrated at scale. The other thing that national labs do is that they host very large user facilities. These are national or internationally prominent research facilities or capabilities that guest researchers from around the world can come and utilize. Maybe some of you have actually been to Lawrence Berkeley Lab to participate in some of the research going on here at one of our 6 user facilities. Well, you might be curious as to why the U.S. Department of Energy got interested in water. And it started, of course, with the realization that water and energy generation are inextricably linked. In the last decade, the United States has faced a series of droughts, and those droughts have impacted the amount of water available for cooling, especially for thermoelectric cooling. And in some cases, the United States has actually had to curtail energy generation because of the lack of water available for cooling. So that was one direct connection that the DOE made, that water is actually critical for energy production. But with time, the DOE began to appreciate that the water-energy nexus is much more inextricably linked. And in fact, that there are places where water and energy cross over. And in some cases, for example, in the generation of biofuels, water is an integral ingredient to producing the feedstocks that will generate biofuels of the future. Similarly, if we are going to capture carbon and store it underground, water might be the vehicle by which we pump that carbon back under the surface. Well, in California, we had our own interesting revelation, how important water and energy were. You may recall that in the last decade, California has had a series of multi-year droughts. And those droughts have prompted conservation measures. The governor at the time, Governor Jerry Brown, passed an executive order in which he insisted that state agencies and individuals undertake water conservation. And in fact, we were very successful. California citizens in California cities and towns managed to conserve 25% reduction in water use. It was a great achievement. Now, California also invests in energy and energy efficiency. We have an agency called the California Energy Agency, and it sponsors a series of programs, rebates, and energy efficiency measures. This chart that you see here is a graph of all the energy efficiency measures that California pays for. And that energy efficiency stacks up to almost 460 gigawatt hours of saved energy. And it's through a variety of programs, including rebates for indoor lighting, building insulation, high efficiency air conditioning and heating, refrigeration, and appliance standards. So there you see all that investment and all the energy saved. Well, researchers at the University of California at Davis looked at the water savings associated with the water conservation program, that 25% water reduction that we achieved during our last drought. And they calculated how much energy was avoided because you didn't have to pump as much water, because you didn't have to treat as much water. And they found, surprisingly, that the amount of energy saved simply from that water conservation was almost equal to all the other energy conservation programs combined. And this taught us something very important. Water is energy. The two are inextricably linked, and you can't efficiently address one issue without addressing the other. So those are the reasons why the U.S. Department of Energy became so interested and motivated to study water, and in particular, desalination. So NAWI, the National Alliance for Water Innovation, is an innovation hub. This is a collection of organizations that have come together for a short period of time to conduct combined research and team science to address a key issue, desalination. The founding organizations are Lawrence Berkeley National Laboratory, where I am, Oak Ridge National Laboratory in Tennessee, and the National Renewable Energy Laboratory in Golden, Colorado. We've partnered with other agencies and organizations such as the Electric Power Research Institute and several California state agencies, including the California Department of Water Resources, the California Energy Commission, and the California State Water Resources Control Board. This map here shows you all the affiliate organizations across the United States. These are either research organizations in green, universities in green, industries in blue, state agencies in purple, and non-governmental agencies in red. Now, this is a 5-year program. It's like a temporary organization. We brought these people together into a virtual organization. The DOE has invested $110 million, and we are focused on early stage applied research to lower the cost and energy of desalination and associated water treatment. Our goal is to develop the next generation of desalination technologies to enable 90% of what we call non-traditional water sources, waters that we're currently throwing away, to achieve pipe parity. That is to say, lower the cost of desalination so that the marginal cost and energy of producing fresh water or clean water from that non-traditional source is comparable to the marginal water supply presently available. Our goal is to secure reliable, affordable water supplies for the nation's industries and communities. Now, you're probably familiar with a research consortium or a research hub. It's a group of research organizations that come together to share results and to build and do joint science. And that's part of the NAWI organizational structure. And of course, we have a wide group of US universities and industries and state agencies associated with that. But we have around that research consortium a larger organization called the NAWI Alliance. This is an open organization. Any organization in the world can join the NAWI Alliance, and we have lists of more than 300 members so far. The NAWI Alliance can listen to and access all the research results from the NAWI Research Consortium, as well as join research teams. Universities and individual researchers are welcome. So this is one way that you can get involved in the NAWI program. Well, before COVID, we had a range of methods by which we got together and planned our coordinated research. We had annual team meetings, and our most recent one in November 2020 was virtual, and we had industry-specific breakout meetings and even events at aligned technical conferences. And we had field trips. Many of our most successful projects are joint projects with water-producing organizations or industries, including major utilities in the United States. Now, I want to shift gears and talk to you a little bit about some of the vision that we have for how desalination can change in the 21st century. Now, if we reflect back, our water systems around the world are a marvel of 20th century engineering. And for the most part, they were built in the 20th century to supply our communities, our industries, and our homes with clean, safe, affordable water. They really are an engineering marvel. But the 20th century mindset of water production was really very limited. We had large, centralized, custom-designed municipal water treatment plants, and we produced one flavor of water, drinking water, that we use for a wide variety of applications. And if you think about it, our 20th century water systems are sort of linear in construction. We start by finding some source of fresh water, sometimes very far away, and we extract it, and we bring it to a centralized treatment facility. At that central treatment facility, as I said, we produce a uniform, high-quality grade of water product, and then we send that finished water out into a distribution system where it's used in a wide variety of environments, including a number of environments where drinking water, quality water, is not really necessary. Nevertheless, this is the quality of water that we have. In the course of using all that water, we bring that water back in a second centralized network to centralized wastewater treatment systems where we treat the water to a condition in which it is safe to discharge, and we toss it back into the environment. Now, this linear system that we've developed is a marvel, and it has led to enormous economic growth over the last century. But it's facing some limits. For starters, climate change is imposing new limitations on the availability and predictability of our freshwater supplies. One scientist said that water is the delivery vehicle for the effects of climate change. And we certainly see this in the western United States, where we have extended periods of drought and a loss of reliable fresh water. For our communities and our cities, much of the water infrastructure below our feet is reaching the end of its life, and we are seeing an increase in cost associated with repair of our water infrastructure. In some parts of the United States, in fact, we have small communities that are so far away from any water supply that they do not have a reliable, safe, affordable source of drinking water. And then finally, we have discharges of pollution and emerging pollutants. And these emerging pollutants are introducing risk, not just to our environment, but also an economic risk to our businesses. In fact, in many situations, our current discharges may represent future liabilities to our industries. Well, all this water is everywhere, but it's not usable. And in fact, the first example of this vision comes back more than 60 years ago from the Kennedy administration, where John F. Kennedy proposed a bold vision to develop science and technology to enable desalination of the nation's salty waters. Now, out of that proclamation in 1962 came a small office within the U.S. Department of the Interior called the Office of Saline Water. And they began to produce research reports to understand the processes of desalination. The fruits of that research you can see everywhere around the world today. Desalination, the most dominant technology being reverse osmosis, produces more than 10 billion gallons of clean drinking water around the world. This is an image of the Carlsbad desalination plant just north of San Diego in California, the largest desalination facility in the Western Hemisphere. But ocean water is not the only salt water that's out there. We produce a lot of salty water. For example, from our power systems. When we generate electricity, we often produce wastewater that contains salts and other minerals that needs to be treated. Our agricultural sector produces large volumes of runoff, water that's either too salty or contaminated to use again, but can't be safely discharged back into the environment. Underneath a lot of the United States, there is salty, brackish groundwater. This is water that's not nearly as salty as seawater, but is still too salty to use directly. And finally, our other industries end up producing large volumes of wastewater, which they spend large sums of money to treat and dispose back to the environment. Now, these non-traditional water sources are geographically widespread. They often contain valuable constituents and are presently discarded. If we could develop new desalination technologies to economically treat these non-traditional waters, we could provide California and the nation with resilient, cost-effective water supplies for the 21st century. So that's our vision. Can we expand the use of desalination? But if we're to achieve pipe parity, that is to say, lower the cost and energy associated with desalination to the point where it's a viable marginal water supply for our communities and our industries, we can't just think about improving the desalination unit process itself. We need to rethink the entire 20th century linear system. And here's why. If you think about water and the cost of producing drinking water today, it enjoys a very favorable economy of scale. That is to say, as we make our treatment plants bigger, the unit cost of producing fresh water goes down. But water is heavy, And when we make very large treatment plants, it also means we have to convey water from long distances into the treatment facility and then back out again into a large distribution network. And large systems end up consuming a lot more energy in conveyance, the pumping cost associated with moving all that water around. So today's technologies create a curve of the levelized cost of water that means that the most sort of cost-efficient plants are of a certain size. Now, we could innovate and improve the unit process for desalination for very large treatment plants, and we intend to do so. But you're not going to overcome the simple fact that water is heavy, and we live on a planet with gravity, and it's going to use a lot of energy to move that water around. So we think that the technology opportunity zone is over here on the left-hand side of the graph, where the unit costs for small desalination plants are high. And the reason is our present portfolio of technologies are mostly oriented towards large plants, and our small desalination facilities are simply smaller versions of larger systems. If you could develop a new set of technologies that were fundamentally more efficient and lower cost, specifically at lower sizes, you'd have a much shallower treatment cost curve, which means you'd have a much shallower levelized cost of water, and you could move the cost and energy associated with desalination down further. But what this also means is that you would enable much smaller distributed desalination. Because one of the most important ways to save energy in the water business is to distribute water treatment and use water over and over again where it is, rather than moving it around long distances. Now, in developing this vision, we ended up identifying 6 challenge areas that we all thought would be valuable places to invest science and technology innovation. And of course, there's an acronym, and the acronym is spelled A prime, and it stands for each of these 6 challenge areas. The first, A, is autonomous operation. We need to develop new sensors and adaptive processes to enable our water systems to be run much more autonomously and much more securely, without as much human intervention. P stands for precision separations. Today's water treatment technologies are very efficient, but they sweep out all the contaminants, even benign contents. We need a new class of precision separations technologies that can precisely remove just the contaminants or just the species that need to be removed for a specific type of water use and leave all the benign stuff behind. R stands for resilient. If we're going to have smaller, more distributed water treatment and desalination, we need systems that can flexibly turn on and off quickly and can accept a wider range of water quality and water volume. Intensified brine management is where I comes in. Of course, you know that in desalination technologies, we create fresh water and we also create a brine waste stream. In many places, this brine waste stream is the most problematic aspect of desalination. It's great to have fresh water, but if you don't have a place to take the brine and dispose of it safely, you do not have an effective process. We need new technologies to safely concentrate brines even down to zero liquid discharge to enable safer storage and transportation. M stands for modular membrane systems. Already, reverse osmosis membranes come in a very compact modular form, but even the range of modular membranes that we have is relatively limited. We would like to see a much wider range of modularized treatment systems involving membranes as well as other complementary technologies. And then finally, the E stands for electrification. Presently, a lot of energy in water treatment is embedded in the chemicals we use to affect the water treatment process. If we are going to have more distributed desalination, we need to develop new treatment steps that utilize only electricity and drive much more of our treatment processes towards an all-electric future. Not only does this have benefits for distribution, but as electricity becomes cheaper and cheaper with the proliferation of renewable energy, we feel this is another way to make water more affordable. So as I said, each of these A-prime challenges will drive down the levelized cost of water. But when you put them all together, you enable smaller scale localized reuse. And that means that you lower the water cost of conveyance. And that's how you can reach pipe parity in a wider range of environments. Now, in some cases, the vision we have for water mirrors a transformation that's already taken place in the energy sector. It used to be that our electricity was generated with large, centralized, custom-designed power plants. They were typically designed over many years. They cost billions of dollars, and you typically had only one per town or city. Today, we still have those centralized systems, but we augment it with a distributed set of energy generation tools, including photovoltaic panels and wind turbines. Rather than being custom designed, these are manufactured products. They have a relatively short lead time, they only cost thousands of dollars, and you can put them on each building. Together, the centralized and distributed systems provide safe, reliable electricity. Just as I said before, if we can generate and reuse over and over again more of our water, it saves not only in treatment cost, but it also saves in the energy cost of not moving the water around. Now, don't get me wrong. We think that A-prime innovations will reduce the cost and energy for large-scale, centralized desalination too. For example, the sensors, models, and adaptive process controls we develop will be immediately applicable to large, centralized facilities. And the precision separations technologies we develop will enable us to harvest waste streams and components from waste streams from current desalination and wastewater treatment plants and upscale those into valuable commodities. And then finally, the developments we have to push electrification in water treatment will enable our conventional water treatment plants to utilize more electricity and to benefit from the revolution in renewable energy generation. From a structural standpoint, there are 4 topic areas in our program: modeling and simulation, materials and manufacturing research and development, process innovation and intensification research and development, and integrated data and analysis. These 4 separate topics work to organize our research program. So think a little bit like a matrix. We have our 6 challenge areas, and the 6 challenge areas are how projects are evaluated. They'll contribute to one or more of these challenge areas. But from a management standpoint, the projects that we choose to fund will be managed around one of 4 of these topic areas. And of course, NAWI is intended to be a hub in the true meaning of the word. Many of the organizations and individual researchers involved in our program are themselves also leading or involved in other organizations and research efforts around the United States and around the world. We hope not only to stimulate research in desalination that we fund, but also help researchers find new sponsors from industry and other government agencies so that we can more rapidly accelerate the pace of discovery and innovation in water treatment. In our 5-year program, we will go through an annual cycle, starting with a road mapping process where we identify key research needs. We will then issue requests for proposals and select projects. We will execute those projects, and as those projects are executed, they will contribute new knowledge which enables us to advance the topic of desalination, lower cost and energy, and then in the cycle we will evaluate what's left to do. In our first year, we already issued our first funding opportunity announcement in the subject of intensified brine management. There was $8 million of funding, and we are presently near the end of our selection process for these projects. This next year, we intend to release a much larger amount of money across all of our challenge areas. We'll be doing this in a series of open calls for proposals in the spring of 2021. We estimate that upwards of $40 million of research investment will be issued. These grants will be for 3-year performance periods. Well, that's it for my presentation. For more information, I encourage you to go to our website at nawihub.org. You can sign up to receive information, and you can also join the NAWI Alliance. It's free, so there's no reason not to join. And once you're a member of the NAWI Alliance, you can get access to all our digital media and content, our data sets, the software we develop, and you can join this marvelous community of innovators who are setting the 21st century goals for desalination and water treatment research. Thanks for your time, everybody. I look forward to our questions and answers shortly.
Well, welcome to this webinar series. I'm Simon Albert from the School of Civil Engineering at the University of Queensland in Australia. And I'm going to talk to you a little bit this afternoon about challenges with water in remote situations. And this is drawing on my group's work across the Pacific, in particular in the Solomon Islands in the Western Pacific. And I thought, given the time of year and the challenges that we're all facing, I'd keep this fairly broad without too much data and the heavy use of imagery, just to really provide a bit of thought-provoking points to try and illustrate some of the challenges that remote communities face accessing water. Now, the Pacific stretches from the Americas across to the Southeast Asia and Australia, and it's an enormous expanse of an oceanic region of the world with isolated islands that are inhabited by rich populations of people in terms of their culture, their livelihoods and their intact environment. And these nations are highlighted, I guess, or typified by the Solomon Islands in the Western Pacific, northeast of Australia, adjacent to Papua New Guinea, where I've spent the last 15 to 20 years working on water-related challenges. Now, when we think of the Pacific, you know, people often have these romantic images of you know, these rich cultures living in seaside villages with a long and proud history of environmental stewardship. You know, that typically these coastal communities on the coastal fringe with, certainly in the case of the Solomons, large volcanic islands that are densely forested in tropical rainforest, and those catchments capturing, you know, up to 3 to 4 meters of rainfall a year. So typically an abundant environment in which to live in terms of water, food, housing, clean air and good health. We have, you know, classic high volumes of fresh, high quality water that these catchments are providing to the local communities. In other cases, we've got low-lying islands, sandy atolls that are only a matter of 1 meter to 2 meters above sea level. In these situations, populations tend to be very dense with limited agricultural land and typically reliant on groundwater and rainwater resources. In fact, some of these populations in Micronesia and the Pacific are some of the most densely populated places on Earth, even more so than Manhattan, believe it or not. The people occupying these islands have a rich traditional knowledge, traditional ecological knowledge of the environment that's been passed down orally over generations. So the way they interact with the environment is built around this deep knowledge and understanding of seasonal patterns, variability, and access to resources, very much in a utilitarian way of providing their basic subsistence needs. These places are also dynamic, incredibly tectonically active, exposed to tropical cyclones, tsunamis, earthquakes, flooding events, and volcanoes. So they can be challenging places that have a high amount of variability. The coastal areas, of course, provide critical subsistence needs in terms of fisheries, transportation, access to building materials from gravel. And these coral reef ecosystems are particularly abundant and rich in high water quality situations. Unfortunately, the Pacific is also a place of active resource extraction, and mining operations, logging operations, and shipping incidents are increasingly, causing significant impacts on these often fragile island environments. A recent oil spill really characterized that, where this spillage of 400,000 litres of heavy fuel oil not only impacted the marine ecosystem, but this oil flowed into the high tide groundwater springs that these local communities relied on. So these impacts can have devastating and long-lasting challenges for the subsistence needs of the local people. And inevitably, the scale and intensity of those impacts can turn these once vibrant coral reefs into relatively barren landscapes. And those impacts are also happening in the terrestrial environment as well, with high rates of tropical hardwood extraction from the native forests, almost entirely exported. These are high value species that are really harvested in what could only be described as a bit of a smash and grab operation, with little consideration given for not only the regrowth of the vegetation, but also the sediment management that's obviously so critical for water quality in these volcanic soil environments. And mining operations facing similar challenges. This is an open cut gold mine that's recently been largely abandoned. And as you can see, the high rainfall environment in these islands makes management of sediment and pollutant runoff incredibly difficult to manage. And you end up leaching not only sediments, but also arsenic and other heavy metals that are typically mobilized with the sediments in these volcanic mining sites. Another example of mismanagement of sediment, in this case loading bauxite ore onto barges. Again, the combination of the high rainfall and the coastal wave action is resulting in significant quantities of sediment being mobilized from the terrestrial system into, in this case, the marine and coastal environment, causing not only short-term impacts on water quality, but as this sediment is resuspended through wave action, these impacts can persist for years often. And all those challenges, can lead to what were once rich, vibrant communities with, strong access to natural resources, good access to bountiful, fresh, clean water. Those combination of impacts can lead to some fairly negative social outcomes where natural resources and water access can be severely limited. And so in many ways, these islands can become really, small-scale mesocosms of the planet in many ways. The sorts of challenges that these these islands face are a small insight into what we as a global community are facing. And so that's what makes these places particularly valuable to understand that transition from, that quite rapid transition from bountiful supply of water, that's clean and available, and through only a decade of intense resource extraction, leading to very limited access to water by these people. And if we think globally about the SDGs, 6.1.1 in particular, which is looking at the proportion of the population that has access to safely managed drinking water services that's accessible, available, and clean. And globally, we know that some regions of the world with particular water scarcity in Africa are struggling to meet these SDGs. And interestingly enough, also, if we look to the Pacific, Papua New Guinea and the Solomons and many other nations in the Pacific are also amongst the most poorly performing globally, despite their 4 meters of rainfall and relatively abundant water resources. Globally, we know that the access to water by the population across the world has been improving dramatically, particularly improvements in Central and South America has led to above 90% access to an improved water source across the global population. And if we look at the green line of people relying on surface water, proportion has been steadily decreasing over time. However, as mentioned, the Solomon Islands is really going against that trend, where we're seeing decreasing access across the nation of access to improved water sources, and we're seeing increased reliance on unimproved surface water, natural waters. And so whilst on one hand, relying on these natural waters can be a wonderful thing. Examples here from the Solomons and Bougainville of this plentiful, fresh, clean water being piped, in this case, by simple bamboo pipes to provide a water point for local people. That can be a wonderful thing in the situation that the catchment and the environment is intact. Unfortunately, however, these surface water sources are highly vulnerable to impact from extractive industries. And so we can transition from an ecosystem service and a natural forested system, in this case a limestone karst environment that's providing a critical ecosystem service in terms of filtering and providing steady, reliable, clean water services to the local population. That can quickly transition with even relatively small amounts of extractive industries such as logging, that can rapidly transition to high amounts of sediment runoff being mobilized from volcanic soils during intense rainfall events. And in this case, that sediment plume washing out of that coastal river into the marine environment. So we've been tracking that transition in the Solomons National Capital, Honiara, which has for a long time relied on a natural underground spring to provide over half of the national capital's water resource that's then piped and pumped across the city of Honiara. This remote sensing analysis over the past 4 years, 2016 until 2020, indicates the disturbance of logging operations within those catchments. And importantly, although the Congolai catchment on the right-hand side of your screen is the major topographic catchment feeding that water source for Honiara, what we learnt based on traditional knowledge of the local people, that in fact the topographically separate Kahove and Kove catchments on the left-hand side of this image, although topographically they weren't connected to the water source. There was underground sinkholes through the karst environment that was delivering that sediment-laden water from logging operations from the Covey and Cahove catchments underground into this water source for the national capital. So despite the Water Authority's best efforts to conserve the logical topographic catchment, in fact, the impacts were occurring underground through these karst environments. And so this really highlights the vulnerability of these water sources to catchment disturbance. And we saw here over the space of 4 years that despite only approximately 10% of the catchment being disturbed, that caused significant impacts on the water quality feeding the town of Honiara. You can see examples from 2016 in panel A across to 2019 in panel B there at the top, the rapid escalation of sediment disturbance through these logging operations, and down below the consequent impacts and result of that in terms of mobilisation through the stream network into the coastal areas. And this is the end result. This is Honiara's national water source. There isn't any filtering service there. It's just goes through basic primary chlorination, which is only effective to a point. Once turbidity exceeds between 5 and 20 NTUs, the chlorination's ability to safely deliver water is significantly reduced, and the nation's capital water supply is often turned off with very little notice. And so clearly having a capital city so vulnerable to these water outages driven by logging is a really, particularly challenging in light of COVID-19 and the increased need for hygiene and cleanliness. And that's particularly challenging when the water is turned off without notice for up to a week. So if we look at some of the data, I did promise you no data, but I had to put some in. So we've worked with the National Water Authority there in the Solomons to install some monitoring equipment in a very remote location that can start to provide this relationship between timeframes of rainfall and the subsequent turbidity peaks into the system. So we can see here fairly moderate, 20 to 30 millimetres every half an hour rainfall event on the 5th of March this year. And we can see within 6 to 12 hours, we have a significant turbidity spike there, which lasts for up to 2 to 3 days before it gradually reduces again. And so over time, we're building up this relationship and understanding a model of the system to be able to provide some advanced warning of the likelihood and the scale and the timeframes of these turbidity events in the system, so that both the Water Authority can prepare, but also the local residents can prepare in terms of filling buckets and rainwater tanks where possible. In other cases, as mentioned, this is a lot more challenging with large abandoned mining pits that are continually releasing heavy metal and arsenic-laden sediments into the natural system. So here we can see on the right-hand side the stream flowing from the mine pit, used by local people for bathing, swimming, washing, cooking, and recreation by children. And unfortunately, if we look at the arsenic concentrations in the surface waters downstream of this mine in the Solomon Islands, we can see that they're exceeding the World Health Organization standards by, often up to 5 to 10-fold above the WHO standard for primary contact. So, these are significant challenges in the case of mining operations because the timescales tend to be decadal rather than these event-driven turbidity spikes that we saw in the drinking water. Once these mining operations have disturbed the sediment and exposed the rock, it can be a matter of decades before natural rehabilitation can occur. So ultimately, we need to be thinking about solutions to these challenges. You know, obviously, we've got in the case of the water catchment for Honiara, the logging operations over that 4-year period delivered revenue to the local people and the national government to the tune of $1 million over 4 years. So a relatively small amount of money that has now led to the water in Honiara being switched off for 20 to 30% of the time over a year. So these are significant disruptions to the local community, and that's now led to the need to build a treatment facility to try and manage that water quality. So that in this case, that treatment facility is going to cost on the scale of $20 million, which is effectively replacing $1 million of revenue that the logging delivered. So, you know, obviously there's a huge amount of scope here for trying to, before this damage is done, trying to capture these ecosystem services in some sort of monetized way, either through carbon credit schemes or traditional payment for ecosystem services schemes that can help facilitate the local communities to protect and conserve this land for the water filtering potential that it's providing. You know, other ways forward that we've been working on is in these remote situations, delivering modern cloud-based water quality monitoring infrastructure that, you know, can rely on fairly low footprint equipment using satellite communications, solar power that can provide real-time access to data, both for the water utility providers, but also for the local community. So with these data interfaces, we can get within seconds of this information being collected, alerts can be pushed to water infrastructure provided, alerts can be pushed to the public that there's a likelihood of a water interruption within the next 6 to 8 hours, and they should prepare themselves. And that relatively simple or relatively small investment can provide a rapid transition to preparedness and increase the reliability of the water. Other opportunities in these remote situations where traditional monitoring, water quality monitoring infrastructure may not be possible. With tailings dams in mining situations, for example, it's near impossible to get access to these tailings dams with boats or personnel. So we've been developing autonomous systems, so using both aerial drones that are able to fly into remote water bodies, winch down sensors or land on the water to conduct water profiles, and then again transmit that data back to infrastructure providers to provide them with some real-time intelligence and understanding of these systems. Other opportunities lie in autonomous surface vessels. So in this case, a small inflatable boogie board sized vessel that has a profiling system that can lower a water quality sensor payload in remote or difficult to access environments that can provide, again, real-time data input and also be controlled to an extent remotely. So these opportunities, both from a technological front and also an infrastructure front, are changing rapidly with the onset of new communications and machine learning and cloud-based computing potential. But at the same time, we mustn't forget that whilst technology certainly plays a role in solving some of these remote water challenges. We need to also acknowledge and respect and utilise where possible the rich traditional knowledge and local knowledge that the communities and people that are living on these islands have had for generations, for tens of thousands of years often. These people have a deep connection to the environment and often have a deep understanding of the sorts of processes, dynamics, and responses that we, with technology, are only just beginning to understand. And so I think that's where some of the exciting work in the future is to leverage advancements in water technology, but partner that with grounded, community-orientated local knowledge to transition away from just chasing the problems to really starting to solve and address these problems in a local, remote context. So thank you very much. I hope that was thought-provoking. I certainly look forward to any discussions around these areas. Feel free to contact me at any stage offline if you're interested in some of these ideas that I've floated today. So I really appreciate your time, and I'll see you soon. Cheers.